Hello physics students. This is a special video in which I'm going to finish up the example problem I started in class. This is example 22.3, field of a uniformly charged rod, and it's based on a problem out of your textbook, chapter 22, problem 32. Brief reminder of what we did in class on this problem. We wanted to find the electric field on the y-axis, which we see is the perpendicular bisector of the rod at a point there labeled P, which is some distance from the origin. The problem labels that distance R, but I'm just going to call it Y for right now, although we have a numerical value for R, 6 centimeters. We also know how long this rod is, L, 14.5 centimeters, and we know it has a total positive charge Q of 7.81 picocoulombs spread uniformly along it. So again, our task is to calculate the electric field vector at that point on the perpendicular bisector. Brief review of what we did, the approach, the procedure. We can't use just the electric field formula for a single point particle because this is not a single point particle. Instead, we have to do basically a thought experiment. We have to imagine breaking up the rod into an infinite number of infinitesimally small pieces, each with some tiny amount of charge dq. And we can treat each one of those little pieces as a point particle and use the electric field formula for a point particle to find the electric field for that point particle. But then we've got to add up all the electric field contributions from all the point particles from the left end of the rod over here at x equals negative L over 2 to the right end of the rod over here at x equals positive L over 2. And the symmetry argument taught us that the electric field vector we're going to get at the point P, because it's on the perpendicular bisector of this positively charged rod, is straight up the y-axis and has a y component only. And I obtained a formula for calculating that y component of the electric field at point P, and it looked like this. I have the charge per unit length, lambda, for the rod. Since it has a charge Q spread out uniformly along its length, the charge per unit length for this rod is its total charge, Q, over its total length. So I have the charge per unit length times that y coordinate for point P over 4 pi epsilon 0. That shows up. That's an old friend. And then we have an integral with respect to the x coordinate, dx, over x squared plus y squared, all to the 3 halves. And the limits on this integral was x goes from negative L over 2 to x equals positive L over 2. That's where I was. And I want to talk about the last steps. One is just to do math and then to finalize with thinking about the physics we've learned. So we have to do this integral. Let me highlight the actual integral part. All right, now that's just a math problem to do that integral. What are your ways to deal with this? Because you are faced with this math problem. And you have, well, I can think of 3 ways to deal with this mathematical problem of doing this integral. One, it's old school, but it's nice and proper old school technique, is to do the integral yourself by hand. You are taught the technique in Math 111, Calculus 2. The technique would be called a trig substitution. Yes, a trig substitution. Another option is to go to a symbolic software program like we have on campus, Mathematica. Mathematica can do many, many, many integrals symbolically. And learning how to use the syntax for Mathematica, enter this integral, and it will give you the result for it. And thirdly, look up the integral in what is called an integral table, which is just what the name implies, a whole bunch of integrals tabulated with the resultant integral for each. If you want to know where there's an integral table that you could use, well, there are many, I'm sure, but you have one in your book. You go to the Wiley Plus, you go to the actual book, and you have to go to one of the appendices. In fact, you want to go to Appendix E, which has a lot of math formulas, as well as amongst those math formulas are a whole bunch of derivatives and a whole bunch of integrals. And you would want integral 19. Now you have to find the integral that fits this pattern. It isn't necessarily going to look exactly like what you've got here, but you've got to be able to recognize its pattern in the table. And then you can find it. It's integral 19. Okay, so however you want to do it, all right, let's say you have obtained the result for that integral. I'm going to come down here and write down what we do next. Let me write it down over here. Okay? All right, so after you've obtained the result for that integral, what do you have? So you've got this stuff out front. Okay, here's the result of the integral. There's a 1 over y squared. There's an x over square root of x squared plus y squared. And then you still got to put in the limits. Now these, remember, are x values. X goes from negative L over 2 to positive L over 2. You got to substitute that wherever there's an x. You got to do the upper limit first, and then subtract, and then substitute the lower limit. Note while we're at it that 1 factor of y upstairs and 1 factor of y downstairs cancel. And now let's go ahead and substitute for the x. Let's keep everything out front that does not depend on x. So now I have a lambda over 4 pi epsilon 0, and I have a y downstairs, then a nice big bracket, and I'm going to substitute in the limits of the integral. First, x equals positive L over 2. There it is in the numerator. And then in the denominator, you have that. I substituted x equals L over 2 everywhere where there's an x. Then I do minus, and I substitute x equals negative L over 2. So I have a negative L over 2 upstairs, and this expression downstairs. Look at the denominators there inside the brackets. They're the same. And notice inside in the numerator, I've got here 2 negatives multiplied together. So that goes positive. And so it's pretty easy to just add those two fractions symbolically. Let's do that. Lambda over 4 pi epsilon 0 y. And what we'll have then is L over square root of L squared over 4 plus y squared. That's our E sub y. Okay. All right, now I found it convenient to multiply numerator and denominator by a factor of 2. You certainly don't have to, but I found it convenient. So then in the numerator, of course, you'll just have a factor of 2 lambda L. In the denominator, I have 4 pi epsilon 0 y. Okay, that red 2 in the denominator, I took it inside the square root down there. That became a 4, and then multiplied it throughout. You get L squared plus 4y squared. Now, one more thing. Look at this combination. Lambda times L. Any thought about what that is? Remember what lambda is, the charge per unit length of the rod. I'm taking that and multiplying it by the total length of the rod. What is that combination? Did you say that's just going to be the total charge Q of the whole rod? Because it is. And then in the numerator and denominator, let's cancel a factor of 2 there. And so here's what we're left with. Q upstairs over 2 pi epsilon 0 y square root of L squared plus 4y squared. Okay? Now remember, we were given numerical values for Q and Y, that's the R, and L. And of course we know epsilon 0, so you can plug in and get a number here, okay? I'm going to write down what you get. E sub y equals 12.4 Newton per Coulomb. If you want to put this in unit vector notation, you would write it as E arrow equals Q times J hat over 2 pi epsilon 0 y square root of L squared plus 4y squared. Okay, so you can also think of it that way. The beauty of this formula is that it's valid for any point y on that, any point p on that y-axis, not just the one where you substitute the value there that's called big R. Any y value on the y-axis. That's why we solved it that way, so that we would have an answer that was quite general and therefore quite useful. Okay, I hope that's helpful. We've done the math. We have solved that problem. We have obtained the expression for the electric field on the perpendicular bisector axis of this uniformly charged rod in terms of the total charge of the rod, the total length of the rod, and where are you on that y-axis, that perpendicular bisector. I now want to do a little more physics and get a little bit more out of this result. Okay, let's get as much as we can. 1, I can use this result to find the electric field on the perpendicular axis of what a physicist would call an infinitely long uniformly charged rod. I know that takes a little getting used to conceptually, infinitely long, but it's certainly something that, the brain can imagine. That rod that's drawn now, that had a finite length before, just goes on and on and on to the left and the right. And it's got the same value for the charge per unit length, lambda, everywhere along it. Okay, it's a uniformly charged, infinitely long rod. And then that y-axis we drew before, right, is the perpendicular axis, and then pick a point at some height y above it, point P. What's the electric field there if the rod is infinitely long? How do we take the answer that we just obtained for the finite length rod and extend it to the case where the rod is infinitely long? It's not hard at all. If the rod is infinitely long, that means the L value is essentially going to infinity. Now, if it still bothers you to think about an infinitely long rod, no problem. Let's just imagine that the rod is very, 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 very long, but not infinite. Finite length, but very long. Then it's still a valid thing to say that the L value is much larger than the Y value. Okay? One length kind of compared to another, and it's the L that's much bigger than the Y. And then take our answer for E before and see how it simplifies in that situation. We'll just take the situation where L is much bigger than Y. The only place where they show up together is right there inside the square root. So if the L is much, much bigger than the Y, the simplest thing to do is to drop the part that has the Y in it. Take that 4y squared that's added to the L squared and just drop the 4y squared. Okay? And then the formula simplifies for E. Okay? E, I'm going to write infinitely long rod, is now QJ hat. Well, I am going to have to go back, I beg your pardon, to one slightly earlier step where I write it as lambda times L. Remember, the Q is that, J hat, over 2 pi epsilon 0 y. Now, for the square root, drop the 4y squared, keep the L squared. So that's all I have inside the square root, L squared. But the square root of L squared is L. So now I just have an L in the denominator. Now you see why I wanted the lambda L in the numerator, because then those L's cancel. And what I'm left with then for the electric field on the perpendicular axis of the infinitely long rod is the charge per unit length over 2 pi epsilon 0 y. Oops, let me get that up there so you can see it. Okay. 2 pi epsilon 0 y. Notice not y squared, just a y, because that's what came out of the formula there, y. And that's quite a handy little formula, okay? And we will use it from time to time. The electric field of a very, 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 very long rod that has a uniform charge per unit length lambda all along it on the perpendicular axis. Notice, by the way, if it's very, very, very long, then pretty much any perpendicular axis is the perpendicular bisector. And you just take lambda over 2 pi epsilon 0 y, and then the direction is, if the rod is positively charged, perpendicularly away, like this, from the rod. Now, if the rod happened to be negatively charged, you could have a negatively charged, very long uniform rod. Which way would the electric field at point P point? It would point directly towards the rod, straight down. So watch out for that too, okay? Okay, so that's an extra bonus result that we got from our work on the electric field on the perpendicular bisector of a finite length rod. We also got the electric field on the perpendicular axis of an infinitely long rod. Okay? You want one other little challenge? I'll give it to you and I'll let you think about it. Go back to the finite length rod, not the infinitely long one, the finite length. And imagine that the point P is way up on the y-axis, so that the y value now is very big. Shouldn't the rod then, if you're very far away from it, start to look like a particle? And then shouldn't the electric field start to behave like that of a point particle? See if you can get this result up above, right up here, for the finite length rod, to simplify for the electric field, simplified to the electric field of a point particle, if the point P, with its y value, is way up on the axis. That's also good practice. Let me leave you with a kind of a streamline diagram so that you can see the electric field pattern at a bunch of different locations near a finite length rod. I used the program Mathematica to make this. The finite length rod is there in red, length L, uniform charge per unit length lambda all along it. It's on the x-axis. The y-axis is the perpendicular bisector. These streamlines show you the direction of the electric field at different places. Okay? Like right on the y-axis, the streamlines point straight up. So the electric field is straight up, as we just said. A little bit over here to the side, the streamlines are curving a little bit away from the straight up direction. So they have some curvature. If you're over here near the x-axis, in fact, if you're on the x-axis, like right here, notice the electric field will be to the right. Or over here, it would be to the left. So we could also find the electric field on the x-axis, okay? That would definitely be doable. But that shows you the kind of a bigger picture of the electric field pattern at a bunch of different locations. Okay, that's an extra bonus video to help you think about solving that example problem that we started in class. And that's all for this video.